Okay, I think we're finally ready to go. Welcome back, everyone. This is the last class before assignment 2 is due. And because it's due so soon, I just wanted to announce something that you may have already noticed if you're observant enough, but assignments in comp sci are usually due at 4 p.m. for the sake of not bothering the tech support guys after 4. But I talked about it a bit with a more experienced instructor, and it turns out that's not actually a rule. They just, or all the profs just set the due date to 4 p.m. for convenience. So the second assignment is actually due at midnight tomorrow. You won't get any tech support after 4 p.m. though. You're on your own for stuff like hand-in and being unable to log into Aviary. So there is still a bit of a cutoff, but the hand-in directory won't actually close till midnight.
Before we start, I have a question about assignments.
For sure. I was actually just about to say, if anyone has any questions about the assignment, feel free to ask during the lecture.
So I had a problem with your stack.o. I couldn't import it from my computer to Aviary. I don't know why. I researched it, but it still didn't work. Could you show me how to do it?
Ooh. I could demonstrate, or at least attempt to, demonstrate compiling the other stacks if you'd like on A.
No, I have an actual problem with getting it to my Aviary directory.
Oh, you're having trouble transferring the file?
Yeah.
Oh, okay. I'll gladly demonstrate that. So the actual file being transferred isn't too important. I'll just demonstrate it with any old file. I'm in the resource folder for this lecture. So let's see. Well, we're going to be working with a file called badcomputer.c during the lecture. It says so on the first slide. So I'll demonstrate transferring with that. So to transfer a file to Aviary, you do SCP, secure copy, I think, secure copy protocol. And then the source, which in this case is a file stored here. So you would do something like stack1.o. And then the destination is very similar to what you use to log into Aviary. UMNet ID at aviary.cs.umanitoba.ca. And then if I do just this, it'll actually copy badcomputer.c to a file called kitzed at aviary.cs.umanitoba.ca. So you have to add a colon. And then after the colon, you can put the path where you want to transfer it to. So maybe I want to put it in my comp 2160 folder. So is that an example of what you wanted?
Yeah, I did the same thing, but it didn't work. I will try it now, and thank you very much.
Okay, yeah, if it still doesn't work, you could ask again during this class or email or office hours or whatever.
I'm sure you're in the right directory, right?
What about directories?
If you weren't in that directory right now, and you just put in badcomputer.c, it would work, right?
No, it wouldn't. You're correct. Yeah?
I have another assignment question for part 3, the packet matching problem.
Okay.
Is there a certain size of the inputs that we're expecting to receive? In assignment 1?
Yeah, I think I'll check the outline to make sure, but I'm pretty sure there is no set limit and that you'll have to dynamically allocate memory to hold the input. Yeah, let's take a look at the outline. I want to make sure that I'm giving you a good answer, plus it'll be a nice reminder for everyone. Okay, so far I don't see anything about a limit either. So I'm like 99% confident in saying that you should be dynamically allocating space for the input. But if you want to make absolutely sure, you could just ask after class, and I'll check the sample solution to see what it does. Any more questions? Yeah.
How do you copy the entire folder into there?
Great question. You still use SCP, but with the -R command for recursive. I'll demonstrate by copying this entire lectures folder onto Aviary.
You're already in Aviary, right?
No, actually, this is local. This is like, I'm just going to copy this so I could get back to it. I guess this doesn't prove much because macOS file paths are very similar to Unix, but yeah, this is local. I'm on macOS, not remotely connected to anything. So yeah, to copy an entire folder, you would do something like this. The important part is that -R for recursive. Just going to run it to make sure I don't have any syntax errors. Yeah. Those files are all on Aviary now. Any other questions? Yeah.
I just have a question. Was the whole Aviary system like used just for computer science students for like courses, or what's its functional use for kind of everyone else?
Ooh. So, if only I didn't procrastinate on my thesis so much, because I do need to look into that because I may need much more computing power to do some experiments. But to my knowledge, Aviary is actually like crazy powerful. Like it has a bunch of really beefy GPUs in it. So it's used for any sort of high performance computing research. I think that's the case. It could just be a contrived school thing, but I'm pretty sure it's the powerful one. U of M definitely has a high performance computing system somewhere. Anything else? I'll just wait a few more seconds before moving on to the lecture. Okay. So we're going to continue to work with strings from lecture 14, and also we're going to talk about debugging, and I have a program prepared that is bad, not for very novel reasons. It's just a classic buffer overflow. So watching me type it and having you code along wouldn't be very valuable. I want to skip straight to actually debugging the thing. So you can find that code file in the course content section for this lecture. So today we're going to talk about debugging. I'm going to talk about some theory about debugging, then specifically show why just spamming printf statements and just generally print statements in all languages can actually lead to misleading output that makes it harder to debug your programs. And then introduce, I guess, concepts for better debugging that'll apply to all languages through showing you how to use a C-specific debugger. The one we're covering, LLDB, has basically all of the standard debugging features that you'll find across languages. And of course, this is going to be continuing to talk about interface and implementation. We kind of can't avoid it. It'll have some stuff to do, or that's specifically to do with C and data hiding. And yeah, that'll talk about implementation hiding some more. Specifically through the static keyword. You've probably seen static before. And in C, it has like a kind of, sort of similar, maybe, meaning than it does, or as it does in languages such as Java. So we'll see the specifics later in this lecture. So, debugging. If you haven't been in this state before, like, how? Now you've probably been here. So you've written code and you have no idea how it works, and maybe you never knew how it works, and it doesn't work. Or maybe you've written code and given it to a friend to test. In this case, don't give them the actual code, compile it first for them. Academic honesty is important. And then it immediately crashes. Or maybe you've been given code by someone else, and it also immediately crashes. They don't understand how it works. So you got to do some debugging. So there are a few strategies that you would already have access to. The most basic of which we call spelunking. And you can also use assert and printf. So spelunking, that's just reading the code, mentally executing the code. It can help to use a pencil and paper, draw a diagram similar to the tape metaphor for memory that we looked at earlier in this course, and then try to identify assumptions that you're making and which are violated. This is honestly the real usefulness of design by contract. You'll likely never write a precondition or a postcondition in the real world, but that way of thinking about what assumptions you're making about the input and output and how they might be broken when the code isn't working, that's something that has personally helped me significantly and will very likely help you all. But of course, spelunking takes a massive amount of manual effort and is so not sustainable for large programs. So we kind of invoked design by contract earlier. Why not go all the way and use assert? So maybe you've spelunked a bit, you sort of understand the code, and then when you have some assumptions, write some assertions to check whether those assumptions actually hold. And this brings up one big part of debugging theory, which is understanding the state of the application. The state is defined as the value of all variables in a program when a program is running. The state applies to a single moment in time. Like if you pause execution, you'll have one state, and then if you run some more code, that'll change the state. Yeah, specific time during program execution, such as a specific line of code. And then I'll talk about this in more detail later, but the counterpart of state is flow, which is basically how the state changes over time. So spelunking might solve your problem, assertions might solve your problem, but what if they don't? Also, if it's not your code, you may not know what the original author assumed. A function takes an int. Do you know whether the author has covered the cases for where it's positive, 0, or negative? I don't know. So your state is that despite adding asserts, the output is still a segmentation fault. Backup plan for the backup plan for our backup plan. You can use printf. So pepper your code with print statements like a block of code, printf reached here, another block of code, printf reached here too, so on. See where the printing stops. So this is something that you could use to better understand the flow of the application. So flow is how the computer moves through the code and how we go from one function to another. So we'll see an example of looking at flow later, but if you've ever gotten an exception in a more robust language and gotten a stack trace, seeing which functions called which at the time of the crash, that's flow. So there's one problem with printf, and that it's buffered. What does that mean? The OS doesn't actually immediately print when you call printf. And this isn't just a C problem. To my knowledge, system.out.print is also buffered and has the exact same problems. So you could force the OS to write after every printf. Does this just not acknowledge what might not happen? It's probably super inefficient. I've actually had a case where I was working on a game and I had print statements printing out debugging information every frame, and they were meaningfully slowing down the game. Like the frame rate was crappy, and I couldn't understand what part of my game logic was slowing it down. It turns out it was a printf, or what's the print statement in C#? Whatever the print statement in C# is. So we're going to, or I'll demonstrate using printf with that bad computer example. I guess I don't have to type the whole thing because you all don't have to follow along this time. Also, I think I pointed this out before, but fish, which is an alternate shell with some extra features that I prefer, actually is available on Aviary. So you could just type fish, and all of a sudden I have cool colors and autocompletion and stuff. So this is bad computer. It has a substring function and a main function that takes or that copies a substring of this really long string to another and then attempts to print both of them. I think I'm going to remove a couple of these print statements so I can add them back later, just pointing out what happens when I add each. So at first it prints out the string, and then it copies the string starting at index 2 into the destination buffer, and max string length is 10. And I know, I'm a theory person, I can't count, blah, 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 but I'm pretty sure that's more than 10 characters. And our substring method, while it does have some assertions that may or may not be helpful, it doesn't do any bounds checking. It does have a loop that eventually terminates based on the length of the input string, but the output buffer is 10 characters long and the input string is way more than 10. We're going to run into problems. Ooh, don't worry about this -G. We'll take a look at that later. It'll turn out to be helpful for debugging. So, compiles without errors or warnings. Great. Oops. So this error message is similar to a segmentation fault and similarly unhelpful. All we know is that Bad Computer is acting badly. So pretend that I didn't just explain the buffer overflow that Bad Computer causes and say, we wrote this completely sincerely and naively and we thought that it would work. So we could try doing some printfs. Note that we didn't get any output before the crash. So the crash must have occurred before any printf statement, right? Does that mean that it occurred before line 27? Well, the only things we did before line 27 are declare some variables, and I'm sure that's fine. So pretty much right off the bat, relying on printf for debugging is going pretty badly. But let's still try adding some stuff. So maybe after substring, we could add that. And maybe a sanity check at the very beginning of the program. Cool. Let's try this again. It's not going to work. No warnings, no errors. No output. What the heck? So this is like, or I'll show you all a Band-Aid solution for these printf woes. And it's that while I don't completely understand the mechanics of buffering printf in C or any other language for that matter, adding a new line seems to make it a bit better most of the time, not reliably though. So I'm going to try adding a new line to this print statement and hopefully we'll get that beginning of program message. Okay, cool. So it worked for that. We were able to print that. Yeah, question?
So I'm a bit confused. Are you saying just sometimes adding that new line for reasons you don't really understand what works?
Yeah, like I could look more into buffering, but the best explanation I can give now is that buffering works in a complicated way, and adding a new line seems to work sometimes for forcing it to output. So we could try adding new lines to the other print statements. Okay, and then it seems to be working a bit better. And so maybe you're thinking you could just use printf for debugging and make sure to include new lines everywhere. Well, for starters, it's not reliable. Trust me on this one. And also, there's at least one pitfall that I can easily reproduce and show you here, and it's that it kind of breaks output redirection. Like, check this out. Wait, I'm just going to make sure there's no output.txt so I know I'm not rigging it. Okay. Yeah. Output.txt exists, but despite having some stuff here, it didn't redirect into the file. That's fine for short programs, but sometimes you might want to use printf to basically log what's going on and then save that log to a file so you can look at that instead of scrolling up and down through your terminal, and that won't work. So I'm not necessarily saying that printf for debugging is terrible and you should never use it. It's great for simpler cases of debugging. I pretty much always use print statements before I move on to a more robust debugger. It's a good tool, but it shouldn't be your only tool. So if printf isn't that good, what now? Yeah, it's bad. Finally, we're at the topic of a source level debugger. So a source level debugger lets you step through your program line by line, which lets you observe the flow, watch variables as they change, so state, and this part's super important, stop execution at certain points using a thing called a breakpoint. So in this course, in this language, we're going to use LLDB, but pretty much everything short of what, or the syntax that you type into the terminal is generalizable for other languages. I've pretty heavily used PDB, the Python debugger, as well as whatever you call the thing built into Visual Studio for C#, C++, and C. And they all have the ability to step, the ability to look at variables, and the ability to set breakpoints. So if you remember that -G from earlier, that is a compilation flag that includes debug symbols in the compilation. That'll make a bit more sense once I actually start debugging. I think I'll do it first with a compilation that doesn't use -G, show you what you don't see, and then I'll use -G and show you all what other information you get. This is different from debug versus release builds, because all -G does is add additional information to the program when it's being compiled. Things like what C code, in this case, corresponds to what binary code, and function names, variable names, stuff like that. Whereas the difference between a debug and release build is more of optimization, where a debug build is less optimized in order to have a greater correspondence between the original code and the binary, while release applies some optimizations, such as disabling asserts. I promise I'll show you all release builds eventually. So to run the program, first you compile it with -G, and then you do LLDB with that program. And it has a variety of commands. Yeah, as shown here. I'll walk you all through it in a moment. But it's kind of cumbersome to have the slides on hand, and the syntax can be pretty obtuse. I bet I'm going to have to look up some syntax at least once during this lecture. So use a cheat sheet. Oh no, this is going to open in the same tab. I don't want that. Oh, and I think I had this one open from earlier. So keep this website open in a tab while you're debugging, and search up what you actually want to do. And then, yeah, this will be super helpful. So for example, maybe I forgot how to set a breakpoint. And there. Now I know that I could do B main to make it stop right before running the main function, or I can also set a breakpoint at a specific line of code in a certain file. So this will diverge a bit from what the slides are talking about, but hopefully this will be a good example of debugging. I have the string class example copied into the debugging example that I have on Aviary. Again, no need to type along. In fact, you shouldn't, because I'm a dum-dum, and I made a change to one of my files. I don't even remember which one. And now it causes some tests to fail. Right, so we got a bunch of successes on the test that we made earlier, but now we have an assertion failure. And we could fix this by putting in a million printfs, but I'm going to demonstrate how to use LLDB effectively. But first I'm going to see if I have -G in the makefile and remove it if I do, because I want to demonstrate how it changes the executable. Oh yeah, I put -Gs everywhere. Oh. And also a helpful tip about make, if you modify the makefile, but don't modify the things like the code files you're compiling, make won't recognize changes to itself. So if you want to forcibly recompile a program, just use make clean before you use make. And helpful tip, for that helpful tip, make clean isn't built into make. It's defined by the make file. It's very common practice to include a clean rule in your make file, and you should do that too. So where were we? We are going to attempt to debug and figure out the root cause of this assertion failure. But first I'm going to do so without debugging symbols and see how far that gets me. It's not going to get me very far. But anyway, LLDB main test. So you type LLDB and the name of the executable that you want to debug. And now we're actually in LLDB's shell, and we can give it commands. LLDB, for better or for worse, has some really concise syntax. For example, I want to run the program, and how'd I just do R? Woo. So this gives us slightly more information than just running the program without the debugger. Seems that the crash happened somewhere in something called pthread_kill.c, line 44, column 76. That's moderately helpful. What I really want is a backtrace, so a list of functions that were on the stack, like the call stack, at the time of the crash, so I could see which of my functions called this pthread_kill thing. And to do that, BT stands for backtrace. So this output looks a bit intimidating. It looks slightly less intimidating if your text is smaller, but I gotta make sure you can all see. So what this all means is that there was a function called GI pthread_kill that was called by another GI pthread_kill, which was called by another one. Maybe it's recursive. It probably just isn't giving me very useful information because whatever code this is probably wasn't compiled with debug symbols. But then these things were called by GI raise, which was called by GI abort, which was called by assert, which was called by GI assert, which was called by charat. Hey, we know charat. So this might not have very much meaning right now because we haven't done anything on frame 0, but we want to be able to investigate the state of frame 7, and to do that we have to move to frame 7. I think I do frame select 7, but as computer scientists we have much better things to do than write entire words, so I'm going to use that cheat sheet and find a more concise way to do this. Cool. Turns out I could just write F and then the number. And this is where it crashed. Yay. I think I can look at variables. No, I can't. Assembly doesn't even really have variables. It's just stuff located at a specific memory address. So, question?
I'm just curious, do you know what that decimal number there is?
This one?
Yeah, I guess any of them, yeah.
Those are the addresses in memory of each instruction. So you'll learn about this. Or have you taken Comp 2280?
I'm in computer engineering, so.
Oh, okay. I would ask, have you taken anything like Comp 2280, but you might not know what that is. This explanation might be redundant to you, but I still want to make it.
Oh, he's right, yeah, I did that one. Yeah, it's 36 there.
Okay,
Yeah,
so.
I've done that then, yeah.
Okay, cool. So yeah, you know about assembly instructions and how they each fit into one address in memory. This is where they are. So yeah, it's a cool little curiosity, but utterly useless for actually figuring out what's happening in the program. So I'm just gonna quit using Q. Confirm that it's okay for me to kill some processes, namely the process that we're debugging. Yes, it's fine. And then I'm going to put -G back. This will give us much more useful information once we get back here. So make, again, when I try to run it, will say that everything's up to date because it doesn't track changes to its own make file. So I do make clean and then make just like before. This gives me an opportunity to show you yet another useful shell trick. You can use and after a command to run another command, in this case, make. So this is just a more concise way of saying run make clean and then run make. It's actually a bit more complicated than that, and I'll try not to go into too much detail, but it's actually pretty cool. That and might remind you of Boolean, like conditional and that's because it should. And if you know about lazy Boolean evaluation, which I think you'll learn about in Comp 2150, it means that the second command will only run if the first command succeeded. So you can imagine success as being equal to true, and then if the first command fails, that's like false, and then it knows the and statement will be false, so it doesn't do the second one. I don't feel like explaining lazy Boolean evaluation, but hopefully, eventually, it'll become clear why they use double ampersands for the command to run multiple commands, and you'll be all like, huh, neat. So yeah, we just make clean, and then make d. So let's try the whole debugging thing again. LLDB main test, run, error message, BT for backtrace, function that we're familiar with at frame 7. And look, it's code. So before, LLDB basically just took the binary code and translated it back into assembly and then showed us that as its best effort of showing the current place we're in execution. With debug symbols, it actually includes the source code in the executable. And that's super helpful for actually letting us see where we went wrong. So this wasn't actually that helpful. Of course, the assertion failure happened at the assert statement. And that's a beefy assert statement too. Something must have gone wrong with the variables. Like one of index, self-length, or char at index must have a bad value. So we should investigate what those values are. To do that, you want to look at the frame variables. Oh yeah, and also if this hasn't reminded you of my memory layout lecture already, frame means stack frame. So frame variable, FRV. And now I have a list of all the variables in this stack frame. So we see index is 0, char at index is capital U. Might raise some red flags. Current is just some pointer, and count is 0. So there's no clear direction on what to do next, even though the problem is totally with char at index. Let's try to investigate self and see if maybe self.length it has a bad value. So to inspect a variable, I use v. And that doesn't tell me any more than it did for the when I pressed FRV. And for the sake of this example, I'm pretending that I think that one of the variables in self has a bad value. So I want to actually look at what the pointer points at. So to do that, I just use the familiar dereferencing syntax, star self. And then it shows us the values of all the struct's properties. So self-length is 0 and head is null. That's another hint at what's gone wrong. So index equals 0, which means that this is true. Index less than self-length. Okay, that's violated. So maybe this part is false, but it's an or statement, so we should check the other condition. Index less than 0 is not true, but it's an or, so maybe this part's true. Index greater than or equal to self-length, that's true because they're both 0. And char at index equals the null byte. So char at index is capital U, clearly not null. So this part of the or statement is false. And we previously saw, since index is not less than self-length, this part's false too. So we now understand exactly, or kind of sort of understand exactly how index, or how the assertion failed, but we still don't know what exactly is wrong with it. So I might keep looking at variables, maybe draw a picture, but we're going to go back to the flow of the program. Char at test empty string. So char_at was called in test empty string, and this is backed up by the fact that our string instance has a linked list head of null and length 0. So it's clearly the empty string. So why the heck did char_at index get set to capital U? It can sometimes be helpful to have your code open in a separate tab. So this was in string list. Line 199. So this is the version that doesn't work. The error that I accidentally introduced is actually on the screen right now. So if you see it, no spoilers, don't shout it out. But I have no idea what's wrong. So I'm just going to set a breakpoint at char_at, and then step through the execution of the function and while checking the values of the variables and see where I went wrong. So how do I set a breakpoint again? I'll look at the cheat sheet. Oh, and before I can do that, I should restart the program, because the breakpoint at the start of char_at won't mean anything when we're already pretty deep into char_at. Oh, no command to restart. I'll just quit and re-enter the debugger. And then before I do that, I just realized or remembered that char_at is called several times during main test. So if I set a breakpoint at char_at, it'll be pretty unhelpful because it'll stop execution much earlier than we want it to. So I was going to set a breakpoint at a more helpful location, but I'm actually going to go ahead and set the bad one and then use that as an excuse to show you a bit more about how to step through a program. So B char_at. I have a feeling I'm going to have to add a bit more information. I'm going to go by file name because I don't really trust LLDB to know where char_at is defined. 166. And then if I run the program, it'll stop the first time it gets to char_at. So if we backtrace, we'll see that char_at was called from test char at general, and we're just going to keep running the program, and it'll keep stopping at char_at until we get to the time when char_at was called from test empty string. So N does a step over, which will execute one line of code while skipping function calls. I think that's not quite what I want. I'm going to just try R to resume. No. I'm going a bit beyond what I rehearsed. I wasn't planning on showing off breakpoints and continuing to run, so I don't quite remember how you resume execution. If it's not in the slides, I'll just skip this part to get back on track. Or no, I'm going to Google it. This might show you good Googling techniques. Oh, this has nothing to do with what I want. Whatever, I'll just set a better breakpoint. So I'll quit, go back into this, breakpoint, and then where will I set it? I'm going to set it to where we call test empty string. $77. Okay, so now we're back on track, and we're going to want to step through the program. There are two different steps you could use. So a single step executes one line of code, which includes going into a function if there's a function call, whereas step over will skip the any function calls it goes through. Skip as in it'll still execute the function, but it won't pause until that function returns. We also call single step step through. So from here, stepping through will enter test empty string, which we want. But if we were to step over, then it would run test empty string without our intervention, and then pause again once it gets to line 78. So now we're at test empty string. And we know that the problem is in char at. So we can step through this line. Actually, we're going to step over because we're pretty sure make string isn't the problem. But let's check it anyway. Okay, empty string has head, null, and length 0, which is basically exactly what we want. So we can now be reasonably sure that the input to char at isn't a problem. Let's step into char at. Note that when we stepped into char at, it paused at the next executable line. Right above here is the function's signature void char at string pointer whatever. So this arrow might sometimes be pointing to what you don't expect, but it's always because it skips to the next executable line. So is anything wrong at the very first line of the code or line of the function? Char at index is capital U still, which it shouldn't be. Of course, this is all contrived and scripted and stuff, but like if you suspend your disbelief a bit, I totally thought that char at index was given a incorrect value at some point during char at's execution, but it turns out the problem is apparent like as soon as you get into char at. So maybe it's not initialized correctly, perchance. Let's look around more in the code. So this is where we're paused in the debugger. And actually, none of the variables had been initialized yet, so I'm going to step through the code a bit more because maybe my not initialized properly conclusion was unfounded. So let's keep stepping. Oh, I stepped into. That means we're going to have to go through check string. I should have stepped over check string. I'm just going to step over everything in there. Okay, and now we're back. I'll step through this as well. And now at this point in execution, all of the variables should be initialized. Let's check on them. And char at index is still capital U. So the problem probably is that char at index wasn't properly initialized. So if we take a closer look, uh-oh, I made a mistake that I probably warned you about as soon as we started looking at C, and that's that I didn't initialize the variable. For the record, the version in the course website does have a correctly initialized variable. I just changed this for the example, so if you had that saved, don't worry about it. But this gives us the opportunity to properly initialize it to the null byte that it returns if there's an error or invalid input. And then let's try running it again. All the tests work. Happy ending. Yay. So that was a demonstration of how to use LLDB. Honestly, at that scope of debugging, we probably just could have used printf to print out the value of char at index, but using the debugger helped us see where exactly the crash happened and, well, why it happened. And actually, I totally take back what I said about printf. It wouldn't have been very useful because I'll just reintroduce the error real quick. So it told us what assertion failed. I was going to say backtrace was really helpful, but I guess this tells you where the assertion is as well. If you have a segmentation fault, as you know, the only output you get is segmentation fault, but the strategy with backtrace, breakpoint, stepping over and stepping through still works. So I think I have another example that just causes a seg fault. Yeah. Oops. Yeah. So like, I think this is my best sales pitch for LLDB. When we just ran a C program that causes a segmentation fault just on its own, the only thing that the output told us is that something bad happened. We don't know where, we don't know with what. But then I did the same with LLDB, and it points out exactly where the segmentation fault happened. And if I wanted some more information, I could do a backtrace, and that'll tell me more about the flow, FRV to get the state. It's great. So I highly recommend at least trying out LLDB. I think I'll post that cheat sheet as another example, or sorry, I'll post that cheat sheet as a web link in the course homepage so that you have easy access to it. It'll be pretty awkward at first as you go from cheat sheet to terminal to cheat sheet to terminal to learn the commands, but once you do, you'll clearly have a much better debugging tool at your disposal. Print statements are still a valid way of debugging and much simpler, so I hope that you try out a real debugger, get good at it, and then develop an intuition for which tools you should use for which problems. So there is some more content in this lecture about information hiding and kind of C-specific, how you can sort of break the interface versus implementation stuff, implementation hiding rather, that we've covered. And then once you've broken it, how to fix it. But we have 5 minutes left. Oh, 4 minutes, the minute just turned. So I'm not even going to bother. This is a nice place to end. We'll talk about information hiding next week. Good luck on the assignment and have a great weekend.